So the plan for this afternoon's speech was going to be to talk about RPKI, but I realised that we've got a whole afternoon, and Tashi from APNIC is going to be giving a quite detailed tutorial about RPKI. So I didn't want to overload everyone with too much RPKI, and I thought I would give a talk that includes RPKI, but it talks also about other parts of the APNIC registry, which are under development and kind of new. So that includes not just RPKI, but something called RDAP. So APNIC's been running as the RIR for many years, as you probably know, for 25 years or so. And actually, as a registry, our job has stayed much the same for a lot of that time, and the technology has also not changed very much over the years. But we actually are going through a few changes now that are going to improve and harden up the registry services so that they're more sort of fit for purpose for the demands of the internet today, which actually have a lot to do with scale and automation and security. So the registry, as I'm going to describe, the registry's got quite an important job to do, but unless we can do it in a way that fits the internet of today, then the registry isn't really keeping up. So this really is about the next generation of registry services. I say next generation, but these new services are here today. So what I hope you'll see with this speech, and also in fact with Tashi's afterwards, is that we've got a lot of change happening that's implemented now, and it's available, and it can make life better, easier, and more secure for all of us, including, I hope, all of you here. I thought I'd start by just talking about what registries are. So APNIC is a regional internet address registry, and there are also other registries in the internet and other registries in the world. Actually, it's not a new thing that to run society properly, there have been registry functions around for quite a long time, because there are various public resources that society cares about, which are outside of the technology space, even going way back, like the land's titles, the right that people have to occupy land, for instance, is another public resource that we all care about. So the idea of a registry or a titles office has been around for a long time, and it's an office or an organisation with some authority to manage and to run the registration of interest and usage of different public resources. So, like I say, land titles or vehicle registrations or phone numbers all involve a sort of registry function, which are quite similar. So when the internet came along, we actually had an existing idea of a public registry being needed, so that the people who are using the internet have got the ability to find out who on the internet has got actually access to, and who's got sort of title or right to use the different resources on the internet that we care about. So those include, and we all know, it's mostly names, numbers, and protocols as the internet registry targets that exist these days. So the protocols, of course, are the resources, the numbers that the IETF uses in creating internet standards. Names, of course, the domain names. So THNIC is a domain name registry for .th, and there are also other global top-level domain name registries. But what we care about at APNIC is neither the protocols nor the names, but the numbers. And so in the internet numbering space, we talk about INRs, or internet number resources, which are IPv4 addresses and IPv6 addresses, and autonomous system numbers. And the idea, again, is that as a registry and as a regional internet registry, APNIC is responsible for running a registry database that allows you to get access to a service and to find out who is using particular internet number resources. And you'd know why you need to do that. I'm sure as most of you are network operators, and you must have used Whois at least from time to time, if not regularly. You need to know who's actually using an IP address, so you know who is who is either attacking you or who is creating some problem or who you need to get in touch with in order to solve some or address some connectivity issue. And also importantly these days, who is the holder of who is the real holder of IP addresses? If you're going to be peering with a network, you need to sort of know and understand who is actually, whether the people who you're peering with have got the right to use the addresses that they're asking you to route. So the registry service, the registry database that's been running traditionally for both name and number registries is something called Whois, and it's really old. It actually goes back to a 3-digit RFC 812 in 1982. So that's before a few of us were born, I'm sure. And Whois is really a very, very basic service that just runs on a TCP/IP port and receives a query actually in any form at all, and it spits back an answer in any form. It's a really basic thing. And so in spite of that, I mean, sometimes simple is good on the internet, and I guess this kind of illustrates that something very simple can be around for a long, long time. But it has outlived its use for a lot of the demands today. And so what we have in the registry world is the need to do better things and to provide a sort of registry service with better facilities. So there's two things I want to talk about here which serve that purpose, serve that aim for different particular applications. So one of them is called RDAP, or the Registry Data Access Protocol, which is really a replacement for the Whois itself, so that rather than a very basic Whois interface, you can use a programmable and a much more sort of modernised way of accessing Whois data. The second of these new services is RPKI, and that's a whole new functionality and a whole new layer of usefulness behind what's a traditional Whois database, because it introduces what are basically cryptographically verifiable signatures. So you can think of RPKI as being like Whois objects, but with a verifiable digital signature. It's not quite exactly that, but that's the way you can think of it. So a Whois object, instead of just being a blob of text, is something that actually can have a signature attached to it, and that you can know through cryptographic mechanisms that object has been signed by the authority for it. So in other words, by the registry. So I'll be talking about both of those things, but first, just to illustrate Whois and how basic Whois actually is. I mean, as I mentioned, Whois is just a server that sits on a port and listens for some text to come in, and that text can actually be anything at all. But if you keep the text in the right format, then depending on the query on the server that you're sending it to, you might get a useful answer back. So there's a command line access to Whois, and if you send it a simple IP address and it is an IP address registry Whois service, then you'll get a response back that if it's, for instance, the APNIC Whois database, you'll get a blob of text back which is in a sort of a conventional format of something called RPSL. The thing about this is if you send the same query to a different Whois service, you could get text back for an IP address in a completely different format that you need to kind of expect in order to do anything with it. Or if it's not an IP address Whois, then you won't get anything useful at all. But you get, in this case, if you send a particular address, you'll get a blob of text back. And we can't do very much with that because it's text and you need to sort of manually parse it, and you need to know where it's coming from in order to actually be able to parse it. All we can do is something like wrap it up in HTML, but our HTML access to Whois just gives you the same blob back exactly, but it gives it to you on a web page. So that's sort of a little bit more friendly, people might think, because at least you've got a web link that you can follow to get that, but it really is not very useful. So really the registry database, it serves a Whois server that spits out something, a blob of text. In our case, for several of the RARs, it comes out in RPSL, Routing Policy Specification Language, and it can go to a command line interface or a web interface, and that's about all. And so it's got a lot of limitations. It's got limitations because it's not standardized, because you have to know what server you're accessing before you know what to expect as an answer. It also doesn't have any authentication or access control. It doesn't have internationalization, so it can only deliver text in kind of US ASCII format, or at least internationalization is not standardized. And it's got no redirection. So as I said, you need to know the registry you're going to in order to know if it can even answer the query that you want. And if you've got an arbitrary IP address, for instance, you don't automatically know which of the RAR databases that might be registered in. So it may be that you've got to try more than one of those registry Whois queries before you find the answer you want. So this is where RDAP, Registration Data Access Protocol, comes in, and it's built as a successor to Whois. It's been built for multiple purposes to serve the needs of both domain name and IP address registries, and anyone who's been involved with the ICANN domain name discussions would tend to know about RDAP. There's a big ICANN meeting going on right now, in fact, on the other side of town or across town here, which is the Global Domains Division Summit. And they've got quite a bit happening over there about RDAP, because RDAP, as I say, it applies to names as well as numbers. But they're the names people, and we really don't need to talk to them so much. As I said, I'm here to talk about the number side of things. But what goes for RDAP in either case is that it relies on something called REST, and Philip reminded us earlier of what REST stands for. Representational state transfer. I don't know if that really helps, but it's a mechanism for taking queries via HTTP, via URLs. And so if you've got a RESTful server, then a RESTful server will receive queries as URLs as additions to the URL string that comes to that RESTful server. And it sends a response back in JSON, which is the JavaScript object notation, which is fairly common these days. And the useful thing about JSON is that a lot of programming languages can just ingest JSON objects and very easily parse them in a very standard way into objects in that language. So that's a very useful thing. The thing about REST being sent over HTTP is that it can get useful things from the HTTP protocol, like it can get access and authentication, it can get redirection and other useful things. It's kind of CDN friendly to some extent, NAT friendly too. So to have a REST and JSON structure behind RDAP is quite useful. What does it look like? Well, here's an HTTP GET command, which shows you at the top a RDAP query as a URL. This is actually the same query as I sent to the Whois server before. It's a query for an IP address which happens to be 210.17.9.244. What you get back, it looks like a blob here, but it's actually very structured. That's a blob of text in JSON, which is the answer, and that's the answer to that query. So that can be sent as a web query. If you have a browser plug-in on your web server, on your web client, that is, you can actually see it in a better structured format. But the point about it is that it's better that JSON response is better for automation. So you can write clients, and here's another web-based client, but it's one that actually takes the result in JSON and lays it out for you because it understands what's in there. And different clients can actually take the results out of an RDAP server and use them in the same way or differently. So there's an RDAP client running at APNIC, and if you go over to LACNIC and have a look at their RDAP client, then you can actually issue the same query to their RDAP client, and it will bring the result back to you. And magically, it's gone and used redirection to find the answer out of the APNIC server without you having to know about that. So that's useful. But where it becomes more useful is that you can build applications out of it. So APNIC built something called Whowas, which is a Whois server that actually gives you the history of Whois, the state of Whois objects over a period of time. And we use RDAP for that. So that's a programmed, an application that actually uses RDAP for what it's good for, which is a programmable service. we've got something called VisAs for visualization of AS numbers. And there's a map of ASs in Thailand. It shows, you probably can't see it, but the cursor there is pointing to something called Symphony. And if you click there, then that application actually brings the data out of RDAP in a structured way. So they're just examples of how, just with that change from Whois to RDAP, you get a whole lot of new functionality, which is very useful for accessing and using the registry in different ways. So RDAP, a bit like this diagram I showed before, instead of using Whois, we're using RDAP instead. It can either come out of the Whois database or out of the back-end registry. It produces JSON, and you can do a number of different things with it. So the benefits of RDAP are quite substantial. You know, we can automate things, as I said. We can do differentiated access. So if there's certain user communities or password protection that's needed to allow access to different communities, then you can do that to allow access to different parts of the database. It's got internationalization and redirection and all of those good modern things. So at APNIC, we've been implementing and working on RDAP since 2015. So it's there and available to you at rdap.apnic.net. We used it to create Whowas. There's some challenge at the moment, which is for across the RIRs, that the 5 RIRs have kind of diverged a bit, I'm sorry to say, in terms of how we are implementing RDAP. And what we will do this year is bring the 5 RIRs together under a common RDAP profile, so that we actually have so we've got properly consistent results across the board. Okay, so that's RDAP. Now I want to move on to the second topic, which is RPKI, the Resource Public Key Infrastructure. And so for the rest of the day, you're going to get quite a bit of RDAP, because Tashi Phuntsho from APNIC is here, and he's going to follow me with a whole lot of technical details. So I'm going to be really talking about the high level. Here's Tashi now. I'm going to be talking about the high level of RPKI, what it's all about, and why we're doing it. And that again is because of the sort of limited capacity or capability of the registry technology we were using before. So Whois just isn't good enough to do a lot of what we want to do with it. And in particular, when it comes to security, a Whois record is only as good as a piece of text which kind of tells you who is supposed to have ownership of a resource, but it's not something you can use automatically very easily. It's something you have to read and understand and then match up with other documentation in order to really trust it. So the point about a PKI framework, a public key infrastructure framework, is it's a hierarchical digital certification system for public and private keys that allows you to have more trust. It's the same system that we use for SMIME, of course, and for SSL certificates. So nobody likes PKI very much. It's pretty complicated. You've got to be quite a crypto person to be able to really work with PKIs, but luckily they're kind of hidden away. So in the case of SSL certificates, you don't really need to do too much with them behind the scenes. You don't need to understand too much about what's happening inside, just to know how to use them. So PKI is around all over the place for those purposes, and RPKI is the Resource Public Key Infrastructure. And it's a set of standards that adds these INRs, Internet Number Resources, into X509 standard certificates. And by doing that, you get a representation of the ownership or the title of the certificate holder to use those resources. And because it's a PKI, it's got a certification hierarchy, and the hierarchy of certification can also follow the delegation hierarchy of IP addresses. So that matches up quite well, and the sort of theoretical model is shown here, where the allocation hierarchy starts with the IANA, Internet Assigned Numbers Authority, at the top, and it goes to the 5 RIRs. So the 5 RIRs receive addresses from the IANA, and the IANA, in theory, issues certificates to the 5 RIRs as a certificate authority for the address space that we hold. Then each of the RIRs, and you can see APNIC in the middle, is then also a certificate authority for certifying the IP address allocations that we make to downstream ISPs or to end entities, to enterprises and users. Something that you see here is that potentially under RPKI, each ISP is also a certificate authority to issue certificates to its customers or its downstream users of IP address assignments. Now, as I said, RPKI or PKIs can be quite complicated, so becoming a certificate authority is not something that many ISPs really want to do. And this is not something that, that is a sort of revenue-generating service or something that your customers are demanding. It's something that you're doing for the sake of improved security. So I'll mention the fact that really you don't need to become a certification authority because APNIC, in the case of APNIC, we can provide that service for you. Okay, I said this is the theoretical model. The practical model is a little different because instead of having a pure hierarchy, we've actually got a situation in place at the moment where there is, instead of one trust anchor at the top, we've got a provision for multiple trust anchors through this system. And that's just the way it happens to have evolved. The sort of reality is that I think the global RIR communities have been a little bit reluctant to see a new hierarchy with a single trust anchor at the top. I mean, this, as you'll see, the RPKI hierarchy is going to become pretty important, and to have a new hierarchy with a new single trust anchor located anywhere in the world is a little bit controversial. So we're actually moving towards a system which is hierarchical in principle, but where there can be trust anchors located in different places. So in the case of APNIC, at least, we've got a trust anchor at APNIC, which is something that you need to recognise in order to rely on or to use the RPKI certificates from APNIC. But there's possibly going to be other trust anchors within the system, possibly at a national level in the case of some countries at least. Anyway, that's just a detail about sort of how this RPKI hierarchy might differ from a very pure single trust anchor hierarchy. Now, the point of RPKI is that not only is it providing you with this digital certification to improve trust and security of the system, but as with RDAP, it's something that can be automated, it's something that can be applied to different purposes. And one of the primary sort of applications of RPKI is about routing security. And in particular, the first step towards routing security is a fairly simple application of RPKI for route origin validation using something called a ROA, which is a route origin authorization. And so a ROA, a route origin authorization, is a document, a record, which actually says that as an ASN, as an IP address holder, you will give authorization to certain ASNs to route your IP address space. And the point about that record is that it becomes stamped, it becomes signed by your RPKI certificate. So it becomes a secure object in itself. So by creating this ROA as a certificate holder, you're telling the world that you're giving permission for certain autonomous systems to route your address space. So that's a very nice example, and it's a current and working example of how RPKI can be applied and be useful. And there will be other examples and other applications in time. But the point is, I think we all know that the routing process often involves just something informal, like a letter of authority between a network and its upstream, so that when the traffic is actually flowing on that route, you may not really know that that traffic is going to the right place. You know, routes are being spoofed more and more often. We heard yesterday that it's actually happening thousands of times a year. And the point of the ROA instead is that instead of a letter of authority, you've got this ROA document, which is actually saying that this autonomous system is authorized to route that piece of address space, and we can all be happier and trust, at least in terms of that route origin, that route origination, that at least it's being done according to the system. There's another smaller application of RPKI which is being developed. It's actually been initiated at APNIC, and it's something called an RTA, or a resource tagged attestation, which is just a fairly simple use of that resource certificate as a signing certificate. So you could take any digital object, any document, you could sign it with your routing, your resource certificate, and providing that the content of that certificate is of interest, and that can be a useful thing. And although the ROA is intended to replace the idea of a letter of authorization or a letter of authority, you could, for instance, use an RTA approach to sign a letter of authority. So my computer's just run out of power, but that actually is pretty much brings me to the conclusion of what I wanted to cover in any case here, which is in the second part, RPKI. I was going to mention the benefits, just to summarise the benefits of RPKI, very similar to the benefits of RDAP as a next generation registry service. We're using a much more standardised and a more detailed approach to provide extra functionality to registry information, to the contents of the registry. And in the case of RPKI, it's performing this really important function of being able to demonstrate in a secure way who are the authorised holders of IP addresses and autonomous system numbers. So that's about it from me. Unless there are any questions, and I'm very happy to answer some, then I think we're going to be moving on to a more detailed tutorial from Tashi about all of the ins and outs and the details of RPKI. So, are there any questions about any of that?
Are there any questions?
That's fine. So,
okay. Thank you so much,
I'll hand over to Tashi. Thank you all.
Thank you so much. Before you are going, I would like to invite Associate Professor Dr. Phuntsho to give you a presentation.
Oh, wow. Thank you.
Thank you very much. For the next speaker, I would like to invite Tashi to proceed the, what is this? The next sections? Yes. RPKI's tutorials. Please welcome.
More
Good afternoon, everyone. Let's continue. I think I'm a little late by about 10, 15 minutes. Continuing from yesterday's Continuing from yesterday's conference talk and today's Paul's keynote, we will just look at implementation aspects of route origin validation, what a resource certificate actually is, right? But before that, some motivation, right? Why even do it in the first place? Some recent incidents. I had one more, but I couldn't get enough time to find out why that happened, so I left it out. But this is from last year, end of last year. I spoke about it yesterday also, where a leak happened somewhere in some part of the world and then it ends up impacting globally, right? So what happened was Google was peering at the ISP at an internet exchange in Nigeria, and an ISP who was peering at that internet exchange ended up leaking out Google's prefixes to China Telecom and other peers at that internet exchange. And given the fact that China anyway does not allow Google content, they ended up blackholing the whole Google prefixes. Right? So for about more than an hour, Google content wasn't reachable. Right? And then, of course, the most famous one, again, I spoke about this yesterday too. This is a very good example of how easy it is to use BGP to actually try and overcome something that is supposedly more secure. Right? Everyone thought that cryptocurrency wallets are very secure. But then what people ended up doing is, instead of trying to hit that, something that's more secure, I try and target something that's not really secure, which is BGP. So that's what they did. Amazon publishes their list of prefixes, and this /21 that Amazon use is for their DNS services, for all the AWS services that they host. So what this autonomous system did is 107.279. What they ended up doing was they ended up announcing more specifics of a /21 prefix that Amazon had reserved for their DNS services, right? And the worst thing about routing is that logic hasn't changed. Whenever a packet comes, we always look at how many more bits can we match, and then that's why a /24, which is more specific of a /21 prefix, ends up becoming the preferred path, right? So it's a more preferred path compared to a /21 that Amazon was announcing, right? And of course, this impact, even if this AS had originated, this /24 from Amazon, yeah. If peers of this autonomous system, if they had filters at their ends, the damage would not have been this big, right? So it seems like none of the networks that were peering with AS 10279 had any inbound filters at their end. And when you have autonomous systems like AS 6939 who are known for leaking out peer-learned routes, so that's what actually happened. There were lots of this kind of AS numbers who were in the middle, who ended up leaking it out to all their peers. And what was the motivation? What was the motivation for that? So it turns out what they did was, like Dr. Paul was saying yesterday, if I control your DNS, I pretty much control what you see. So the reason why they hijacked this was, now any query, any DNS queries that come now gets responded by this hijack network. And in this case, what were they looking at? They were specifically looking at myetherwallet.com. So any queries that came for that domain, they got answered, and they got IP addresses which belong to these two autonomous systems in Russia, right? So every time I query myetherwallet.com, since the DNS is now already hijacked, the responses that I get back says, okay, here is your myetherwallet.com. Right? They give you an IP address that they control. That still should not have made it possible for me to get into a cryptocurrency wallet. And that's where the problem exists with this automated cert issuers these days. If you look at root certificates sitting on your browser, Let's Encrypt is a very good example. We all promote Let's Encrypt so much, but how could somebody actually get a valid certificate for a domain that they did not own, right? So hijacking BGP is one thing, hijacking DNS prefixes, answering wrong, giving wrong answers to queries, but then being able to make it seem like it's a valid domain is another thing. So our guess is somebody was using an automated cert issuer like Let's Encrypt to get a certificate issued. Else, it's not possible, right? Even if I hijack your prefix. And then, once I convince you that this is a valid certificate, then you pretty much trust me, right? So to summarize, what actually happened was I hijack Amazon's DNS service. Every time somebody queries, instead of sending it to the right DNS, since I control that prefix, I give you an answer that I want. I redirect you to wherever I want. I have got valid certificates. Your browsers think it is valid. You type in your credentials. I use that credentials to actually go and empty your cryptocurrency wallet. So $17 million in 2 hours, like I said yesterday, is a very nice early retirement package, right? Not so recent. I discussed about this yesterday. Also, entity OCN, which is the domestic network of entity for Japan. And as all of us do, whenever we peer or whenever we cross-connect with CDNs, we tend to generally announce our more specifics. Instead of me announcing an aggregate, if I have a /19, I would try to announce all of my more specifics to the CDN so that that is the most preferred part. So from entity side, I think they did the right thing. But then Google, 15169 AS, they leaked it out. Right? They leaked it out to all their peers like Verizon, a tier 1 network, and then Verizon leaked it off to all its other peers, right? So what this shows is, first thing, Google didn't have outbound filters. Second thing, Verizon did not have inbound filters with Google. Right? And there was no max limit. Forget max limit. They didn't even have prefix filters, right? If there was a max limit, because normally Google would be seeing about 50 prefixes, but that day they saw about 25,000 prefixes. That's a big jump. If I should have, normally we encourage people to have a limit to the number of prefixes you accept from your peer. If they had that threshold configured, there would have been some alerting or some warning that would have popped up in Google's NOC, right? So what happened that time? So this is the impact. This is before the leak. Right? Before the leak, Japan to Japan traffic, it's obvious 10 to 15 milliseconds latency. But during the leak, here is Japan to Japan. The leak happened somewhere in San Jose, right? So after the leak, Japan to Japan traffic first gets routed to West Coast US and then comes back to Japan. Right? So close to 300 milliseconds latency. And then people thought, okay, is it just Japan that's getting hit? And entities that prefix between entities started testing their prefixes in Europe also, the same in Europe too. Europe to Europe traffic gets routed to the West Coast and then comes back to Europe, again adding that many latency, right? And of course, the most famous one, like Aftab said yesterday when I started off talking, I was saying, for a company, I think your reputational damage is more critical than technical damages, right? This incident happened so long ago, 2008, 11, 12 years ago. And then we still talk because this is a really good example, right? The government had mandated that Pakistan Telecom not allow YouTube in the country. So what did they do? They actually blackholed YouTube's prefix, and then they started announcing a more specific prefix of YouTube was /24. YouTube had a /22. So globally, everyone was seeing a /22 from Google, and they were seeing a /24 from Pakistan Telecom. And because of longest matching best path selection of routing, everybody thought that's the best path. Let's all send our traffic for YouTube to Pakistan Telecom. They had a black hole running in their network. So YouTube was knocked out. So with BGP, it is so easy to knock out anyone. Right? If I don't like someone, I could pretty much try and announce their routes, black hole everything in my network. It's possible. It's easy to do. Right? And as I mentioned yesterday, the reason these things keep happening is there is no way we can identify a bad update. Right? It does not come with a special tag. It looks like a normal BGP update. Right? It has the right attributes sitting in it. It has the right prefix sitting in it. When I receive it, it looks like what a regular update looks like. So that's the problem, right? And again, like I mentioned yesterday, for those of you who attended it, in cryptography, I think the problem comes from the fact that there is no security layer in TCP/IP. Right? We don't have a security layer in TCP/IP, meaning we end up doing patches at every layer. If there is an application vulnerability, patch it. If there is a transport vulnerability, come up with techniques like TLS, SSL, right? If there is a network vulnerability, come up with techniques that fixes issues, vulnerabilities at each layer. There is no security layer in TCP/IP, right? So what's happening? So as with everything in cryptography, since you can't identify what is bad, what do? We try and identify what is good, right? In most of the cases of cryptography, generally it's the use of digital certificates which tend to prove that whoever has that certificate or that key pair is the true owner, and whatever you say is true, what someone else says is not true, right? So you try and identify what's good, and then you filter out the rest, right? This is just for fun. And I don't know why should we care, because like I mentioned, with BGP, it is so easy. Right? It's just so easy to do so much damage. How do we address this? Any sane network engineer who runs a network should be doing all these things. Right? If I have a downstream customer, I should be filtering them. Right? Look up what prefixes they have. Only allow those, don't allow anything. If I'm peering with someone at an internet exchange, or irrespective whether I'm doing a direct peering or at an internet exchange, find out what resources they have authority of, allow those resources and filter out the rest. Right? The only difficult part when it comes to filtering is when you talk to upstream. If I am receiving the whole internet feed from upstream, then it becomes really difficult to filter because there are just so many routes. So with upstream, the technique is a bit different. What we do is we filter out what we shouldn't see, like bogans, right? Special addresses. I don't want my own prefix also to come from my upstream. So filter out those things, and then I accept everything else. But with your peers and with your downstream customers, you should be able to filter what you want and then filter out everything else, right? And not just normal filters. Have a limit. If my peer has a /19 prefix, what's the maximum number of prefixes that they would be able to send to me? Allow the aggregation. They might want to do traffic engineering. So if they have a /19, maybe 2 raised to 5, about 32 prefixes. And don't allow more than that. So that even if they're leaking someone's prefix to me, the damage is controllable. Like we saw that Google leaking out entities' prefixes. If Google had some form of prefix limit with entities peering connection, usually they see 50 prefixes, all of a sudden I see 25,000 prefixes. The limit should have prevented that leak. The same applies for AES-path filters. For more granularity, you end up using prefix filters, but for general filtering, you can filter things based on the AES-path also. Right? And it's also good to have AES-path limit. Our APNIC chief scientist, Jeff Houston, his research shows that on average, the internet is about 5.7 AS deep, meaning about 6 autonomous systems deep. But like Dr. Philip was showing earlier, you saw how some people prepend so much, right? They prepend their autonomous system so much. And sometimes, if you look at the internet routing table, you see 50 to 60 AS pretends. What that does is it takes away a lot of your memory also, because you need to store those attributes of a particular prefix in your router. So all of a sudden, you end up spending quite a bit of money on buying a beefy router. You need more memories, you need more CPU, right? And do things like, and when it comes to route leak, the way BGP works by default, Aftab also mentioned this yesterday, by default, BGP is permissive. What does it mean? Default is allow, default is permit. Right? So if I'm configuring a peering session with her, configuring a peering session with him, without me telling anything to BGP, BGP starts sending things, advertising things. And that's how route leaks happen. Right? I have 2 upstreams example, and as I'm configuring BGP with the 2 of them, the moment my BGP session comes up, things start leaking. Her prefix goes to him, his prefix goes to her, without me telling it to do anything. Right? That is BGP's default. So to overcome that default, the industry has come up with RFC 8212, which says by default, BGP should reject. Right? Don't be permissive. But the sad part is not many operating systems support RFC 8212, right? From Cisco's side, only iOS XR does this. Nokia's SROS, maybe 15 dot something only does it, 19 dot something only does it, and Bird Routing Daemon does it. Other than that, there are no routing operating system that supports RFC 8212. So what do? So you can come up with a hack, right? If I'm configuring a BGP session with the gentleman here, bring up the session, kill it, and then I configure things. First shut down the session, configure things, configure my export, import filters, apply the filters, inbound, outbound, and then bring up the BGP session. So that way I prevent leaks. So basic BGP hygiene needs to be done, right? And currently, what do? Somebody wants to peer with me, I receive a peering request, I do what's called a legitimacy of address check. I should be doing, people may not do, right? I assume people do this, and we should be doing this. Example, if Anna wants to peer with me, I can't just blindly trust whatever she sends me. Whenever I receive a request from her, I should be doing a legitimacy of address check. Confirm that that resource belongs to that organization or that particular individual. Once you know that it belongs, then you create filters according to that, right? And then you apply your filters inbound and outbound. So that's the current way of doing things. And a bit more detailed look at the legitimacy of address check. First one, whenever I receive a peering request, and they say, okay, I would like to peer with you, these are my IP addresses, these are my AS numbers. So how do? So I manually verify, right? I look up the Whois database. Whenever regional internet registries delegate resources down to ISPs, that record is maintained in a database, a delegation database, right? Which is called the Whois database. So you look up the Whois database. I'm not so sure if you can see the command, but you look up the Whois database. Anna wants to peer with me. She says this is her prefix. I look up that database and make sure that that prefix is actually being delegated to her, right? I look, I say, oh, I see there is INRs, which indicates it was indeed delegated down, right? And whom was it delegated to? It was delegated to APNIC training in this example. Right? So manually verify that that resource was indeed delegated. The next one is what I still don't understand, right? The letter of authority concept. It is not security. It does nothing. Does not create filters on my routers. It does nothing. It just guarantees that should things go wrong, you're safe. So absolve yourself of liabilities, I suppose, where if I want an upstream to announce my prefix, they might ask me to give them a letter of authority which says, Tashi, as a holder of this resource, I authorize this network to announce my prefix on my behalf, right? So it's just a letter of authority. And the third and the most common one is the routing registries, internet routing registries. So what these databases are, so they would have routes, their origin AS, and if you have multiple peering, it would also show inter-AS routing policies. Right? So whenever I receive a request from someone to peer, they would also be looking up this internet routing registry database and see if there is a route object that already exists there. If it doesn't exist, some ISPs are really strict. They'll say, go create an entry first, right, in this routing registries. And once you create that entry, and the entry the most important entries are your route and route 6 objects. And if you're a big ISP with lots of downstream customers, bless you, with lots of downstream customers, you also create proxy aggregation objects like AS set objects. So I look up that, and the idea of internet routing registries, it allows me to auto-generate filters. Right? The idea being, whatever is in that routing registry, I'll accept. What is not, I will not accept. Does that make sense? So that's why you get told to create route and route 6 objects, because then I can automate filters. Accept what's in the INR database. Whatever does not exist, don't accept it. Right? So it makes it simple. So here is an example. I'm using a RPSL tool called BGPQ3. You can use other RPSL tools, IRA tool sets, RTconfig. So in this example, I'm creating a prefix list called peer v4in, and I'm trying to create it for autonomous system AS17660. It auto-generates that Cisco syntax prefix filter for me. It just generates the filter. You don't have to manually create it, but you still need to push that filter to your device for sure, right? It just generates it for you. The below one is with that 6 option, I'm saying generate an IPv6 filter, right? For that peer. So it generates that filter. By default, BGPQ3 does Cisco iOS syntax. You can specify bird, you can specify Juniper. If you have bird, specify the B option. If you have Juniper, specify the J option. So Junois, it'll generate those filters for you, right? And this is an example if you are pairing with someone who has lots of downstream customers, right? In this case, I'm using an Australian ISP called Superloop. So they have lots of downstream customers, lots of autonomous systems behind them. So you can't create prefix filters individually because then your filters would be very long, right? So instead, you use an object called the ASSet object, and then I generate ASPath filters based on that object, right? So from ease of usage, from automation perspective, it helps. But again, the logic, you need to know what this tries to do. The logic is I will accept whatever is in that database, and I will not accept whatever is not there. So with that logic, what if I have not created any entry in any routing registry database? Right? Are you going to not accept anything from me? So that's the problem with routing registries. First thing, there is no authority model. There are just so many routing registries out there, right? How do I know? If you look at the most common routing registries are RDAP, right? And the oldest. Anyone is able to create an object there. It does not have to be me, the owner of the resource, who creates. Anyone can. That's the problem. So how do I know that entry is genuine? That entry was created by someone who owns the prefix. There is no way I can verify that. So there is no authority model. Right? Last week I was in Myanmar, and there was an ISP there, YTP, right? They were asking me to help them create Whois, and as we were looking up RDAP, as we were looking up route objects in IRA databases, there was a very old entry for 2 of their /24s in RDAP. Right? So that's the problem. You have those historical records that, and address transfers do happen in the region, right? So maybe somebody had created it before you got that resource, and nobody had cleaned up that database. Now, the problem with that is if I'm trying to auto-generate filters using that dirty database, my filter is also dirty then, right? My filter is only as good as the accuracy of the database. That's the problem. And there are just too many. Anurag had a presentation in Myanmar last week. He said there are 25 routing registry databases, 25. So which one do I trust? There might be entry in one, there may not be entry in the other. So which one is correct? Right. So that's the problem. Incomplete data. And this, because there is no incentive for many ISPs to even, smaller ISPs to even go ahead and create these route objects. Right? The logic of filtering using IRR database is I accept whatever is in the database and I don't accept whatever is not in the database. But with that logic, if you don't find a route object in a routing registry database, does that mean that object does not exist, or does that mean I didn't create it? Right. So you can't confidently, what I'm trying to say is you can't confidently create or auto-generate filters and rely on it completely, right? So you need some other way of verifying that. And this is scaling. I can create, auto-generate filters using RPSL tools with normal peers, with my downstream customers, but with my upstream, there is no technique. If I am buying transit from entity, example, and if they're giving me the whole internet feed, my RPSL tool is useless. Right? Because I can't auto-generate a filter for 750,000 prefixes V4 and 60,000 V6 prefixes. So it just doesn't scale. So just a word of caution for those who are still using IRR filters. I'm not saying it's bad, right? Just need to make sure that you verify that the data that sits in those databases are good data, right? So what you can do is, the way it works is, there are the 5 RIRs. They allow you to create those route objects and route 6 objects in their own IRR databases. And the good thing about the RIRs is, if you don't have the authority or if you don't have the credentials, you can't just go and create entries, right? Whereas in RDAP, I can go and create. All I need is a maintainer object that looks like it belongs to me, right? So my suggestion is, if you still want to do IRR-based filtering, at least create your objects in authoritative databases, right? Because that gets mirrored. That gets mirrored to well-known databases like RDAP, right? So it is timely, it gets synchronized there. And if you're generating RPSL filters, pointing it to RDAP, please make sure you specify the source option, right? With BGPQ3, if I give the source option, it will generate filters using RPSL, but it'll only look for authoritative sources. I can mention source APNIC or source, right? Or source ARIN. It'll only generate filters based on route objects that are from those databases. Okay, if you're using RTconfig, there is also a source option, right? So that's using existing tools. That's looking at existing tools. So coming back to the question of, since I can't identify what is bad, let me try and identify what is good, right? So the idea being, we already have working cryptographic applications out there, PKIs, right? You go to a website, you get a digital certificate from their website, which contains what? It contains the public key of that particular domain, which is signed by a root certificate authority, and your browsers already come with root certificate authorities installed in it, right? That's how you do HTTPS. That's how you trust a web server, right? So similarly, can we use digital signatures? Example, the problem with most of the route hijacks is, if he's announcing a prefix, how do I know he is authorized to announce that prefix, right? We need to be able to confirm that. So can we use digital signatures to say, if I own a prefix, let's say 1.0.0/8, if that prefix belongs to me, I should be able to authorize any network to announce that prefix on my behalf to the global routing system, right? And as we are very familiar with PKI, can we borrow the same concept using digital signatures, right? What is a digital signature? It uses key pairs, right? It uses asymmetric encryption techniques, a private key and a public key. Public key is public, and with the private key, I can sign things. And whoever receives my signature can verify my signature using my public key. So can we borrow that same idea, right? Because people are already familiar with. So if I can digitally sign and say, hey, this is my resource, I authorize this autonomous system to announce that to the BGP routing table, right? So I sign that. When you receive that BGP update, you receive that and you also receive a signatures, and you can say, can I verify? So you can digitally verify and say that, okay, indeed, this AS is allowed to originate that prefix, right? So that's the whole basis of RPKI, right? It's a very simple idea. Can I use digital certificates to sign that authority, right? But then the problem with anything is you need to validate. If I receive a BGP update with a signature, I need to be able to verify that signature. And how do I verify? If you encrypt anything with your private key, I'll use your public key to decrypt that, and that proves that you signed it, right? So that part is the easy part. But the difficult part is, how do I know that that public key is yours in the first place? Did you take someone's public key, right? So I need to prove that. I need to prove that up the chain of trust, right? When you look at current HTTPS, TLS or SSL, that's how it works. We have root certificates who are self-signed certificates. And if you have a domain, you just prove to them that that domain is yours, they will give you a certificate. And your certificate contains your public key, which is signed by their private key, right? Whenever you send me a certificate, I use your public key to decrypt it, and to verify that the key belongs to you, I go up the chain of trust to the root and say, hey, is this public key this person's? The root says yes, right? So how do we build that? In names, it is quite complicated. Look at your browser. How many root certificates exist? So many. Right? And there are some very weird root certificates also out there. Who signed? Did you guys read that news? About 5 years ago, there was a root certificate authority who went ahead and signed zones, domains like facebook.com, google.com, github.com. Right? So they are now no more. Their root authority has been revoked. So that's the problem with names. There are just too many authorities. But when it comes to numbers, there are only 5 RIRs. Yes? For North America, you have ARIN, South America, LACNIC, Africa, APNIC, Europe and Middle East, RIPE, Asia Pacific, APNIC. So there are only 5 who can delegate resources down to end users. Right? So it's a much simplified root hierarchy. Right? So to build that trust, we could actually we can actually replicate our delegation hierarchy. At the moment, theoretically, INR gives the RIRs big chunks of address space along with ASS space, and then the RIRs delegate this down to end ISPs, right? So we could use this same delegation hierarchy to build the chain of trust, right? And how do we build that? Paul has already touched upon this, right? Theoretically, INR is the one who gives big chunks of address space to all these 5 RIRs. And it's this RIRs who give or delegates this address spaces down to end ISPs. So we can use that same delegation hierarchy. We use what's called a resource certificate, right? So if I'm a RIR, whenever I delegate a resource to someone, let's say I'm delegating a resource to Anna, I also issue a resource certificate along with that delegation, which proves that, hey, this resource has been delegated to her. And that resource certificate is like any digital certificate. It has a public key signed by my private key. Since I am high up in the chain, I sign and say, hey, I have delegated this resource to her. And to prove that, I give her a resource certificate, which has a public key, which is signed by my private key, right? So that's what resource certificates are all about, right? This is a quick recap. If you look at all the digital certificates that you see, don't look at anything. Just, if you look deeply, you will see that all it has is a public key. It binds, it associates someone with the public key. It proves that that public key is your key. And how do I prove it? It is signed by a root's private key. There is a digital signature attached to it. Right? So we borrow the same concepts for numbers. Still use the same X.509 digital certificate, and we do RFC 3779 extension. Right? Instead of just signing names, now we can also do an extension, put IPv4 or v6 addresses there, and also the AS number. So whenever I delegate something down, I'll say this IPv4 address, this v6 address has been delegated to this particular organization, and I issue a digital certificate of it. Right? So the theory goes like, whenever some authority issues or delegates a resource, you have a resource certificate, which proves that whoever has that private key is the owner of that resource. Let me simplify it, right? So now using that certificate, now that I have a digital certificate, now I can go ahead and say, okay, this AS number is allowed to originate my prefix. It's as simple as that, right? And for routing purpose, I'm saying my this prefix 61.45.248.0/21, I allow AS 17821 to originate to the global routing system. And that's what we call route origin authorization. Me, as the owner of that resource, I am authorizing a particular network to announce it on my behalf. That's why it's called authorization, right? So to put it simply, we have been talking about whowas, route origin authorizations a lot. To put it simply, it's nothing but a digitally signed object. Right? I'm saying that this particular prefix, in this case the /19 prefix, max length says deaggregation up to this level. From a /19 up to /24, I am authorizing this AS number to originate it on my behalf, and I digitally sign it. That's it, ROA. All this theory, I should have just used this one slide, and it would have been much easier, right? But please remember, multiple authorization can exist for the same prefix. If I have multiple upstreams, example, if I'm a downstream customer, a very stubby network, and I want to authorize this AS number and this AS number to originate on my behalf, I can do it. Only the owner of the prefix can do it. If you have downstream customers, do not create ROAs for them. They have to create the ROAs. Me as the owner of the prefix, I should be the one authorizing AS1 and AS2. I authorize both of you to announce it. So multiple ROAs can exist for the same prefix. Okay? So with all that theory, what can it actually do? At where it stands as of now, it can prevent misoriginations. It can prevent someone trying to hijack my route, like Pakistan Telecom trying to hijack YouTube's route. Because Pakistan Telecom went ahead and announced YouTube /22/24 prefix, and the world thought it was their prefix. So we can prevent those kind of misoriginations or route hijacks. Okay. So what are the components of RPKI? First one is the issuing party. So those are the certificate authorities. Like any PKI, like any public key infrastructure, you need the trust anchors. You need the certificate authorities who issue the certificates. So those are generally the regional internet registries, or in some cases, big ISPs. They are also certificate authorities. Please remember that the difference between a regular PKI and resource PKI is every certificate that gets issued actually has certificate authority capability built into it. It's whether you want to use it or not. Right? So if you're in the APNIC region, you go to your My APNIC portal, type in your credentials, you go ahead and authorize, you go ahead and create ROAs of your resources, your prefixes, and the issuing party, APNIC as the issuing party, will then push this ROAs to a publication repository, right? And then the second component is, now that you have a issuing party that issues all these ROAs and all these digital certificates, you need a tool that can pull all these things. And that's what we call a relying party. Or in other words, this is the RPKI validator. It's a tool, it's a software tool. Its job is to pull ROAs, route origin authorities, from all the global repository, right? So this is what it does. This is your relying party. Or in technical terms, we tend to call it a RPKI validator. Its job is to pull ROAs from all the global repository, and it keeps it maintains a cache of that. And this is the beauty of route origin validation, I think, compared to path validation. Cryptography stops here. No more crypto from this point towards my router, which means my router can be cheap, which means I don't have to spend so much money, right? The vendors may not be that happy, but me as someone who is running a network, definitely happy. This is just a quick information for everyone. You have two kinds of models. You can do the hosted model, where your regional internet registry or the certificate authority maintains everything for you, publishes the ROAs for you, and all you do is you just create your ROAs. Or some also do the delegated model. Under APNIC, we also have those national internet registries like JPNIC, TWNIC, CNNIC, and others. So many of them, they do the delegated model, where they are the CA for prefixes that they give in their region. Okay? Not so important. Most people would be doing this. Right? And putting all these things together, this is what route origin validation looks like. Right? The issuing parties, they will publish your ROAs that you create. If you deploy a validator, that validator will pull all the globally created ROAs, and it maintains a validated cache. It maintains a cache, right? And like I said, your cryptography stops here. Then on your network, this is your network. On your network, not on every router, only on your edge routers, your border routers, your peering routers, your transit routers. You configure it only on those routers. Don't have to do it on every router, right? You do it on those routers from where you learn routes from others. So basically, those are your border routers, right? So what you do is, on those border routers or edge routers, you go ahead and configure what's called a RTR session, RPKI to router session, right? It's a single line command. Not difficult at all, right? It's a single line command. Configure that. The moment you configure that, so what it will try to do is, like I said, cryptography stops here. So it will pull a copy of this validated cache and it will keep it in the router's cache memory, okay? And the memory consumption is not much. It's about 30. At the moment, since there are not many rows, it takes about 25 to 30 meg of your router's memory, okay? It keeps a cache here. So in this example, there is a row 24066400::/32 up to a length of /48, and the origin AS is 17821. So it takes a copy of that, keeps it in the router. Now, when this border router receives updates from its eBGP peers, right? In this case, when this router receives an update from this AS 17821, and the update it is receiving is 2406:6400::/48. It receives that before it accepts it, before it uses it for any BGP best path decision-making process, it will now compare it against a ROA, a copy of ROA that you have. When it receives it, it will say, okay, hold on, let me check the ROA cache. And it look up a ROA. It'll say, is there a ROA for this prefix? Right? So what you will look at is, you will first look at the prefix itself, 2406:6400. Okay, it matches, prefix matches, good. It will next look at the max length. The max length is up to a /48 here. What you receive is a /48, good. And then you will look at the origin AS. In this case, the origin AS is 17821. Your ROA says the origin AS is 17821. It's a valid ROA. So your BGP router will now tag that route as a valid route, right? Or it might tag it as an invalid route. What's invalid? The prefix is okay, but the origin AS is wrong. If someone is hijacking your prefix, their AS number could be different AS, so that is an invalid route. Or your prefix length may not match. And this is very important, right? You might have a /19 and you advertise that to a global routing system. I might break that or deaggregate that into more specifics, and if I announce a /24 to the internet, I become the best path, right? So that's why you also check the max length. Even if the prefix is correct, if the length is not correct, it will mark that as an invalid route, okay? And the other state, of course, is not found. I receive a BGP update. I want to compare that against a ROA cache, but there is no ROA to compare against, and which is 80% of the global routes that we see all come as not found because people are too lazy to create their ROAs. Right? So please create your ROAs. You don't have to do this. This is route origin validation, this whole thing. But what you can do is at least log in into your My APNIC portal and create your ROAs. It costs you nothing. 3 clicks. Right? 3 clicks of your life. 1, 2, 3. Right? So the least you could do is do that. Right? 80% of the global routing system is not found. That shows we have 80% network engineers who are too lazy. Right? Okay? So let's do a quick test. Here is a ROA. Right? What's the prefix? 10.0.0/16. What's the max length? /18. So it syncs up from /16 to /18. What's the origin AS? What's the origin AS? 65420. Okay, that's a ROA that I see. Now let's have a, so that's the ROA that you see in your validated cache. Now let's see what you see in BGP. Let's say in BGP you receive this route, BGP update from your neighbor. What do you think? What do you think this is? Is it valid, invalid, or not found? Valid, invalid, or not found? That's a smart one. Come on, anyone. Valid, invalid, or not found? Valid. Okay. Why is it valid? The prefix matches, the length matches, the origin AS matches, right? Straightforward. No nonsense. Yes, Arnold. Arnold gets a ROA t-shirt if we have, no? How about the second update? How about the second update? Yes, why yes, the prefix, does it match? 10.0.0, 10.0.128.0/17. It's because of the max length, more specifics, right? And the origin AS is same, valid. Good, everyone is concentrating. How about this? How about this BGP update? Invalid, sure, you are awake. Why invalid? Origin AS is wrong. Someone is hijacking your prefix. Fine, that's good. How about this? All right, Mike, why? Max length, right? Somebody is trying to leak a more specific of your prefix out to the global routing system, right? Prefix is okay, the origin AS is okay, but the max length is not okay. So it is invalid. How about the last one? Okay, I have a valid, a loud valid from a big fella. Okay, I have a wrong AS, that means invalid? Are you saying it's invalid? Right. So, whenever I receive a BGP update, if I'm doing route origin validation, I'll compare that against a validated cache of whowas that exist. So in this case, I receive a BGP update 65430 origin AS. I look up this prefix, I look up my whoa. There doesn't even exist a whoa for this particular routing update that I received, which is 80% of the internet is currently this. Not found because people are too lazy to create whoas. In APNIC system, it is 3 clicks. Those days, 2014, when we were, few of us experimenting, I was still working in Bhutan Telecom that time. When we created whoas, it was quite complicated. But the backend has been simplified to that level where now it's 3 clicks. First, those days you have to generate a certificate first. Once you see the certificate, you have to pull in the certificate, then go ahead, look up your resource, create. Very complicated. Now, log in, click. Here is your resource, specify, type in the max length, type in the origin AS, you're done. Right? And APNIC's RPKI system at the back end is tied up to a route management system also, which auto-generates route objects for you. So you don't have to manually create both whoas and route objects. Okay? So, what could we do with all this validation state? Okay, your router says valid, not found, right? Invalid, not found. So what can we do with that? First one, do nothing. But up to you. We are just trying to list out the choices that we have. Possibly you want to observe. You start doing route origin validation. You want to see how many are valids, how many are invalids, how many are not found. And you might want to investigate further why it's invalid, right? Sometimes it could be invalid because someone is trying to do something bad, or it may not be that case. It could be some mistake somewhere, right? You want to verify those things. Second one, if you have downstream customers, or if you're an internet exchange, right? I, for one, don't want someone to decide for me. When I used to run Bhutan Telecom's core network, I never liked it when upstreams tried to decide things for us. Let me be the one deciding. So in that case, if you have those kind of downstream customers, you could at least, if you're doing route origin validation, and if they are not doing it, you could at least tag those prefixes, right? You can actually tag those prefixes. Here I'm using a standard community tag. You can use BGP large communities if you want, right? You could go ahead and tag this route and send it down to your downstream. Let them decide what they want to do. Or even at Internet Exchange, if you don't want to drop invalids, you could do this tagging. This is the best practice RFC 7115, where instead of dropping invalids, people suggest that you play with preference value, local preference. Valid gets the highest preference, not found gets medium preference, and invalids gets the lowest preference. So you're trying to isolate those small part of internet that is invalid to a very, to an unpreferred list. Yes, Mike. Exactly, theoretically, yes. That's your choice, right? And me, I can't tell people what to do, right? We can talk the technology. I can say, this is how you see it. But again, it's your choice. It's your network, right? What you want to do with it. There are lots of options. The third one is, of course, the last one is drop them, right? So I'm just listing out the options. It's your choice what you want to do with it, right? There are networks who are dropping it already. AT&T since February started dropping it. And we actually had few cases where few small ISPs in India had a problem because AT&T had started dropping invalids. And they had reachability problems because there are lots of non-residential Indians living in the US. And they had reachability problem and they had approached our help desks to fix those invalids. So it's a good thing that few networks are blocking. And then if you look at the number of invalids, it's about 6,000 prefixes, right? So not much. Out of 760,000 V4 prefixes, about 6,000 prefixes are invalid. But again, I don't want you to come back to me after 1 week or say, hey, you told me to drop invalids, and all of a sudden, what if, when you look at a net flow of your network, and what if 80% of your traffic goes to one of those invalid prefixes? Yeah, exactly. Right? So I leave it to you. But then, of course, like you said, drop the invalids. There are networks that are dropping it. There are internet exchanges that are dropping it. It's a choice that you make. It's a call you make. And I think that's a very good call. I'm just trying to be safe here. Here is an example of AT&T dropping it. While we were at Apricot, they decided they will drop invalids. Here is our friend Mark Tinker from Africa dropping invalids. 2 ISPs. CCOM is probably the largest transit provider in Africa, Mark Tinker. So he started dropping invalids. And this was Aftab's joke yesterday. Their announcement said we will drop it from 1st April. Everyone thought they were playing a joke. And then they actually dropped it on 5th April, right? So it wasn't a joke. They actually dropped invalids. Right? So go ahead. You can drop invalids. But like we discussed, with route origin validation, it only validates the origin autonomous system. It is not at all difficult for me to spoof someone's origin autonomous system. If there is a peering session between Arnold and Anna, and if I'm in the middle, I could spoof your AS, announce something to Arnold, and if Arnold is doing route origin validation, it'll come as valid because the AS matches, the prefix length matches. All of a sudden, I receive traffic that was meant to go to you. Spoofing origin AS is not difficult. What is difficult is trying to hijack a session that already exists. That is difficult. But if I manage to hijack that session, spoofing an origin AS is not difficult, right? So that's why, theoretically, the next thing in this big puzzle is what's called AS path validation, right? Not only origin validation, but people say to be secure, I need to now start validating the path itself. So that if somebody sits in the middle and tries to spoof your origin AS, that path is not valid and Arnold will not accept it, right? So this is what we call AS path validation. And some people also call it BGP-sec. So theoretically, it's a very easy concept, and I'll run you through that concept, right? Remember I said that there's this concept of resource certificates. Whenever we delegate resources or RIRs delegate resources, RIRs also issue a resource certificate. And this is what a resource certificate looks like. Here is your V4 address, here is the origin AS, the autonomous system I delegated to you, and here is your public key, which is signed by my private key as the RIR, as the trust anchor, right? Now you can use this for, first is route origin authorization. We just saw that. You can use this certificate and say, hey, I authorize this AS to generate this prefix, right? In this example, you can create a ROA using this resource certificate. The other one is you can use that to sign AS paths. If this is one path, if I'm announcing to this eBGP peer, I can sign the path that I have made announcement to this AS. If I have a second link, I can sign this path. So this is called AS path validation, right? So the way you do it is the AS plus the router ID. Example, if this is a border router, so I can use that to sign the path. And theoretically, it's as simple as this. In this example, the border router in AS1, when it sends a BGP update to the border router in AS2, it's signing that path using that same resource certificate, right? Now, when AS2 receives it, AS2 wants to announce that to AS3 and AS4. So what it will do is when it announces that same update off to its neighbors, it signs on top of the previous signature. So you end up creating a chain of signatures. And then if I am someone sitting next to AS3, when I receive it, I'll look at the update. I'll see whether there is a ROA, first thing, whether the origin AS is valid. And the second thing, I will then start verifying the signatures one by one. Right? So theoretically, this is a very good concept, but in theory, right? Because with route origin validation, cryptography stops at the validator. But with this, cryptography now comes to your router. I need to maintain all those certificates. I need to verify each and every signature that I receive with each and every prefix that I get, right? Normally in BGP, when I send a BGP update, I can send more than one prefix, yes? Or do I just send one prefix? No. I can group a prefix that has similar attributes, put them all in one BGP update, send it across, right? But with AS path validation, I can't do that. It has to be per prefix, right? So this is the problem with AS path validation. First thing, too hardware intensive, right? I need more CPUs, I need more memory because cryptography is on the router. Right? Second thing, there is no mechanism to distribute these certificates and these keys, right? The concept is there, but then there is no mechanism. And the most important one is this. With origin validation, even if rest of the world is not doing it, I can do it, nothing breaks. But with AS path validation, can I have an unsigned path in the middle? Let's say we two agree to do AS path validation, but you don't agree. So all of a sudden I have an unsigned path. How do I overcome this kind of unvalidated paths? That means everyone pretty much has to do it with AS path validation. No wonder there is no deployment of AS path validation. In theory it exists, it's a great idea, but in practice it doesn't exist. So that is RPKI. I don't know what the time is. Is it time for a break? We'll come back to the second session where we will do a simple, I need to set up the lab. I'll ask you to deploy some validators. Thank you, let's take a break.
Thank you very much, Mr. Tashi. Is not finished. He is not finished. Yes.
No.
We will start our coffee break first. May I suggest you for 2 shots of espresso and a piece of spring roll outside? Yes, it will be better for you because I saw you that you are so sleepy now. 1 shot is not enough. You can request for double shots. Okay, and we'll meet him again within, I think, 20 minutes. Okay, thank you.
This thing ran out fast. I knew it was one. It ran out fast and fly. Maybe I tried to find the ThaiNOG, but I still was one. Anyway, I was about 3 or 4 seconds.